The oldest light in the universe came back wrong. A bruise pressed into the southern sky. 5 independent measurements, all pointing the same direction. Galaxy clusters a billion light-years away are drifting towards something that does not exist inside the observable universe. Somebody predicted it in 2006, and the math checked out. Following this, all the way to the end took me somewhere I was not ready for. We are sitting on a ledge, and the floor is somewhere below us. Something has been pressing against the edge of everything from outside. It left marks. If this is the kind of investigation you finish, subscribe and leave a like. Let's begin. In May 2009, the European Space Agency launched a machine called the Planck satellite. It cost roughly $700 million to build and had one job: look at the oldest light in the universe. The engineers designed it to measure temperature differences of millionths of a degree, making it the most precise thermometer in human history. Nothing before it had been so sensitive. Nothing aimed at the CMB had ever returned data this clean. What is the CMB? 380,000 years after the Big Bang, the universe had cooled just enough for the plasma fog to lift. Before that moment, the cosmos was opaque, a dense, searingly hot soup of charged particles that scattered photons in every direction, like light bouncing around inside a thick cloud. When the fog cleared, photons streamed outward for the first time in every direction, at the speed of light. They have been traveling ever since. We call this ancient glow the cosmic microwave background, and it has been cooling for 13 billion years. By the time it reaches our detectors, it sits only slightly above absolute zero. The Planck team released their map in 2013. Every cosmologist alive was waiting for it. The map was supposed to confirm what the standard model of cosmology predicted, that the oldest light in the universe is smooth, nearly featureless, statistically identical in every direction. A gentle hum with no pattern, no preference, no axis. The Copernican principle, the idea that no place and no direction in the universe is special, depends on this being true. The entire mathematical architecture of modern cosmology depends on it. The map came back wrong. Here is what wrong means. The CMB temperature varies across the sky by roughly 1 part in 100,000. Tiny, nearly imperceptible fluctuations from one spot to the next. The kind of random variation you expect from quantum noise in the early universe stretched to cosmic scales by inflation. The Planck team mapped every variation with extraordinary detail. When they analyzed the results, they found that the fluctuations are not random. They are not statistically identical in every direction. The map has anomalies. The Planck collaboration published these findings honestly and clearly, described them as statistically significant, and acknowledged in their official literature that these anomalies challenge the standard cosmological model and have no agreed-upon explanation. That is what $700 million and 3 decades of satellite observation brought us. The most precise picture of the early universe ever taken returned with features that should not be there. 3 independent satellite missions, spanning more than 2 decades. COBE, WMAP, and Planck. Different instruments, different teams, different eras. All 3 confirmed the same anomalies in the same regions of sky. 3 independent detectors produced the same result. 3 independent measurements pointed at the same problem. What were the anomalies? There are 3, and they build on each other until they reach something that should be talked about far more than it is. I am going to take each one in order. What you need to understand right now is that every anomaly we are about to examine was sitting in the data, confirmed, statistically significant, and officially unexplained before anyone proposed an answer for it. The universe laid out these clues without being asked. We built the most sensitive instrument in history to read the beginning of time, and the beginning of time came back wrong. The Planck team, to their credit, did not pretend otherwise. There is a cold patch in the southern sky, a specific region, roughly 10 times the width of the full moon as it appears from Earth, sitting in the direction of the constellation Eridanus. where the temperature of the oldest light in the universe is about 70 millionths of a degree colder than the surrounding sky. 70 millionths of a degree sounds like almost nothing. Here is why it is not. The entire CMB varies by only about 1/10,000th of a degree in total. The cold spot's deficit represents 3 to 5 standard deviations below the average, a deviation so extreme that if you ran a computer simulation of the Big Bang 10,000 times, using correct physics and correctly randomized initial conditions, the statistical expectation is that none of those simulations would produce a cold region that large, that cold, and that smooth. You would have to run hundreds of thousands of simulations before getting one that matches what we see. Because the CMB is the edge of the observable universe, the last surface from which light could escape before reaching us, 46 billion light-years away, that 10-degree patch of sky corresponds to a physical region roughly 1.8 billion light-years across. To give that scale some weight, the Milky Way is 100,000 light-years wide. The cold spot's footprint is 18,000 times wider than our entire galaxy. Whatever produced it was operating at a scale so vast that the entire local observable universe would be a footnote inside it. The chain of logic here needs to be walked through explicitly. In the standard model of cosmology, CMB fluctuations are the imprint of random quantum variations in the early universe, noise that got stretched to cosmic scales during inflation and eventually seeded all the structure we see today. Random means no preferred locations, no preferred directions. The cold spot is exactly what a random process should not produce. The only question, when you find something this statistically improbable, is what physical mechanism produced it. That question was taken seriously immediately. The cold spot was first identified in 2004 from WMAP data by Vielva and collaborators, who published their analysis with the statistical case laid out clearly. Cruz and colleagues confirmed it with independent analysis not long after. Then Planck confirmed it in 2013. 3 independent datasets across a decade, pointing to the same feature in the same location in the southern sky. The cold spot has a name that understates what it is. A cold spot sounds like a sensor artifact, something that will be explained away in the next data release. What it actually is, the most statistically improbable feature in the oldest light we can access, confirmed 3 times by independent instruments, with no physical explanation from within the standard model, is more accurately a bruise, a mark pressed into the universe before it was finished forming, large enough to span 1.8 billion light-years of space, and cold enough to stand 3 to 5 standard deviations outside everything physics predicts. The field has been sitting with this for 2 decades. The name kept it quieter than it deserves to be. We are probably living in one of the rarest possible configurations of our own universe, unless something other than chance produced it. In 2015, a team at the University of Hawaii, led by a physicist named Istvan Sapudi, made an announcement. They had found the largest known structure in the observable universe, a supervoid, an enormous region of space almost entirely empty of galaxies, roughly 1.8 billion light-years across, located exactly where the cold spot is. Science publications ran with it. The headline was irresistible: "Mystery solved." Here is how a supervoid produces a cold region in the CMB. When photons travel through a dense region of space, they gain energy as they fall into the gravitational well and lose it again, climbing out, arriving with roughly the same energy they started with. But when photons pass through an underdense region, the gravitational well is shallow. The photons cross it, lose a small amount of energy to the expansion of space during the crossing, and arrive slightly cooler than they would have through denser territory. This is a real, well-understood physical process called the integrated Sachs-Wolf effect. The right size, the right location, the right mechanism. The relief in certain corners of cosmology was audible. It lasted about 2 years. In 2017, a physicist named Ruari Mackenzie at Durham University ran the numbers with rigor the initial announcement had not. What Mackenzie calculated was this: the supervoid Sapudi found is real. Its location is consistent with the cold spot, but its depth and density profile are not sufficient to produce the temperature deficit we observe. The supervoid accounts for at most 20% of the cold spot's anomaly. The remaining 80% has no physical explanation within the standard model. What remained, once the mundane exits had been closed, were explanations that sit outside the standard model entirely. Either something happened to this region of the sky that the standard model does not contain, or the standard model is wrong about how quantum fluctuations behave at the largest scales. Both options lead the same direction: outside. Outside what the equations describe. Outside what any internal process can generate. The most statistically improbable feature in the oldest light we can see had no exit from within. The door had been locked from the inside. The significance of Mackenzie's finding cannot be understated. Science advances by proposing hypotheses and testing them against the evidence. The supervoid was a real, testable hypothesis that made specific, quantifiable predictions about how much temperature deficit it could generate. It was tested with better data and better methods than the original announcement had used. It failed by a large margin. 80% of the anomaly had no candidate explanation remaining. That is not a small residual to mop up with additional refinements. That is a gap so large that whatever fills it must be either unknown physics or something that acts on our universe from outside the standard model's domain. Mackenzie did not speculate about which. He stated the result and let it stand. The field has been sitting with it since 2017, and the gap has not narrowed. Right now, the CMB is arriving at every radio antenna, every sensitive detector, every electromagnetic receiver on the surface of this planet. It has been doing this since before our planet existed. It surrounds us completely, reaching from every direction in the sky, carrying the oldest information accessible to any instrument humans have ever built. And it is asymmetric, not dramatically, not in a way that shouts from the raw data. Subtly, statistically, at exactly the level of precision that only the Planck satellite could confirm with certainty, the entire southern hemisphere of the CMB sky contains systematically more variation, more power at large angular scales than the northern hemisphere. The south is not cold in just one spot. It is structurally different from the north in a way that runs across every large-scale feature in that hemisphere. If the universe has no preferred direction, this asymmetry should not exist. An isotropic universe, one that looks the same everywhere and in every direction, should produce a CMB that is statistically indistinguishable between its northern and southern halves. The probability of the hemisphere asymmetry we observe occurring by random chance in a truly isotropic universe is approximately 1 in 10,000. Both WMAP and Planck confirmed this independently, using different instruments and different analysis pipelines. Here is the chain I want you to follow. The cold spot is one anomaly in one region of the southern sky. We just watched the mundane explanation for it collapse. The hemisphere asymmetry is a different anomaly from a different analysis, using a different statistical framework. It operates at a different scale. It also points south, 2 independent anomalies, confirmed by 2 independent satellite missions over 2 decades, pointing in the same direction. That is not one unexplained feature. That is the beginning of a pattern. Cosmologists have a word for what it means when your universe has a preferred direction, violation of the Copernican principle. The Copernican principle is not a philosophical preference. It is built into the equations of general relativity that describe the large-scale universe. It is built into every cosmological calculation ever made about the origin and structure of the observable cosmos. If it is wrong, if the universe genuinely has a preferred direction, then a significant part of the mathematical architecture of modern cosmology needs to be rebuilt from scratch. Some researchers argued the hemisphere asymmetry might reflect poorly modeled local effects or incomplete foreground. Subtraction. The Planck collaboration ran every systematic check available. The asymmetry was not instrumental. It was not a foreground artifact. It was in the data at high confidence, and it remained unexplained. The Planck team's 2015 and 2018 data releases did not resolve this. Successive improvements in sensitivity confirmed the asymmetry more precisely than any previous analysis had allowed. More data, better instruments, higher resolution. The anomaly strengthened with every upgrade. The community moved on to other questions because there was nothing more to say from within the standard model. The asymmetry had no explanation. It still does not. Two anomalies, confirmed independently, pointing the same direction, with no agreed-upon physical cause. The cold spot is localized, a specific region, a specific cold patch. The hemisphere asymmetry is structural. The entire southern half of the CMB is systematically different from the north at the level of large-scale power distribution. One of these could potentially be dismissed as an extreme but possible random fluctuation. Both of them together, pointing the same direction, discovered by different teams using different analysis techniques across different missions, is a different kind of problem. The probability compounds. A 1 in 10,000 event multiplied against a 1 in hundreds of thousands event begins to look like evidence rather than chance. The universe does not seem to know it is supposed to look the same everywhere. Imperial College London, 2005. A physicist named Kate Land and her collaborator, João Magalhães, published a paper analyzing the largest scale structures in the CMB, the longest wavelength fluctuations, the ones that span the entire visible universe. These are called the quadrupole and the octupole, technical names for the universe's biggest features, structure at scales so vast that the distance from the Milky Way to the edge of the observable universe would fit within them many times over. They should point in random, unrelated directions. There is no known mechanism in the standard model that would cause the two largest features in the observable universe to orient themselves toward a common axis. They are oriented toward a common axis. Land and Magalhães found that the axis bisecting both patterns is aligned on the sky with a precision that, they calculated, had a probability of occurring randomly at roughly 1 in 1,000. They named this the axis of evil, a name that is playful and accurate in equal measure. What they were describing is an axis of preferred direction in a universe that is not supposed to have one. Here is the part that received less attention than it deserved. The axis of evil points toward the ecliptic plane, the plane of Earth's orbit around our star. An alignment with a local structure would normally suggest the signal is contaminated, that the measurement is picking up something nearby rather than something cosmic. Land and Magalhães considered this carefully and could not rule out the possibility at the time. The most precise measurement of the early universe ever made is not consistent with the foundational assumption of the theory built to describe it. Here is what the scientific community did with this information. The Planck collaboration noted the alignment in their published papers, flagged it as anomalous, and left it unresolved. There was no press conference. There was no headline stating that the bedrock of modern cosmology appears to be failing at the largest scales we can observe. The finding was formally acknowledged, moved into the category of known anomalies, and the field continued using the same foundational assumption the data had undermined. Because there is no alternative, you cannot rebuild the entire mathematical architecture of modern cosmology on a foundation you have not yet found. So the field kept using the old one, while the data sat in the record pointing at a problem no one had a solution for. Land and Magalhães named it the axis of evil. The name was a deliberate provocation. Something in the universe has a preferred direction, and it is aligned with the structures closest to us in the sky. in exactly the way you would expect if something nearby or beyond the boundary was orienting the cosmos around it. The Planck satellite confirmed this. The field did not have an answer. The axis remained. Here is my position on coincidences in science. One anomaly in one dataset can always be dismissed as a statistical fluke. Two anomalies pointing the same direction in two independent datasets begin to require an explanation. Three anomalies confirmed by three independent analyses over 2 decades of satellite observations, all pointing toward the same region of sky, is evidence that something real is happening. The probability of 3 independent anomalies aligning by chance compounds with every addition. 1 in 1,000 times 1 in 10,000 approaches 1 in 10 billion. Physics does not like those odds. Neither do I. Let me put the 3 pieces side by side so the pattern is visible. The cold spot is in the southern sky, in the direction of the constellation Eridanus. Confirmed by WMAP in 2004 and by Planck in 2013, statistically improbable at 3 to 5 standard deviations. No mundane explanation as of 2017. The hemisphere asymmetry shows the southern half of the CMB sky has systematically more large-scale power than the northern half. Confirmed independently by both WMAP and Planck. Probability of random occurrence roughly 1 in 10,000. The axis of evil is an alignment of the 2 largest scale patterns in the observable universe along an axis pointing toward the southern ecliptic. Confirmed by Planck in 2013. Probability of random occurrence roughly 1 in 1,000. These were found by different teams, using different techniques, working on different features. Nobody was looking for a pattern. The pattern assembled itself. There is a physical mechanism that would produce all 3 anomalies simultaneously. It requires something outside the observable universe to have interacted with ours during the early inflationary period. Something with a direction, a gravitational reach, a mass large enough to suppress structure formation in the region of sky, facing it, and induce coherent large-scale alignment in the CMB. That something would have to exist beyond the horizon of what we can see. But the marks it left would be exactly the marks we find. This is the moment in the investigation where the question changes. Before this point, the question was, what caused each anomaly? After this point, the question is, what caused all 3? The first question allows separate, mundane answers for each feature. The second question compresses all 3 anomalies into a single unknown source, and that source has a direction. Something, at a scale larger than the entire observable universe, appears to have a direction. That direction is embedded in the oldest light we can see. We have not yet looked at whether this pattern extends beyond the CMB. We have not yet considered whether anything else is moving. Here is what I find most unsettling about the pattern as it stands. Each of these anomalies was discovered by a different research group, working on a different feature of the CMB using different analytical tools. None of them were looking for the others when they found what they found. The cold spot was a temperature analysis. The hemisphere asymmetry was a power spectrum analysis. The axis of evil was a multipole alignment analysis. 3 separate methodologies, 3 separate teams, 3 separate features. The same direction. The compounding nature of this is exactly what makes coincidence untenable as an explanation. The universe is telling us something with repetition, and the repetition is pointing south. In 2008, an astrophysicist named Alexander Kashlinsky at NASA's Goddard Space Flight Center published results from a survey unlike anything his field had attempted. Kashlinsky and his team analyzed several hundred galaxy clusters, the largest gravitationally bound structures in the universe, assemblies of thousands of galaxies held together by enormous halos of dark matter, each containing more stars than there are grains of sand on all of Earth's beaches. They measured where these clusters were, and then they measured something more important, how they were moving. The technique Kashlinsky used is called the kinetic Sunyaev-Zeldovich effect. When CMB photons pass through a galaxy cluster, the hot electrons in the cluster's gas leave a distortion in the microwave background that encodes the cluster's motion toward or away from us. By measuring these distortions across hundreds of clusters, his team could determine whether the clusters showed any coherent drift, any common motion that could not be explained by the ordinary gravitational pulls of the mapped matter around them. This is the kind of analysis that only makes sense to perform if you suspect something unusual is happening, Kashlinsky suspected. Here is what he found. Across a survey region roughly 2.5 billion light-years across, hundreds of galaxy clusters are moving in the same direction, not randomly, not towards some local attractor that can be identified within the observable universe. All of them drifting together toward a point on the sky near the constellations Centaurus and Vela at roughly 2 million miles per hour. Kashlinsky named this dark flow. Consider what 2 million miles per hour means at this scale. A conventional aircraft moves at roughly 500 miles per hour. The fastest spacecraft humanity has ever launched travels at a few 100,000 miles per hour. 2 million miles per hour, sustained across hundreds of galaxy clusters, separated from each other by millions of light-years, all moving in the same direction, is not explained by local gravitational structure. Kashlinsky's team published follow-up results in 2010, extending their survey to the limits of their detection range. The signal persisted. There was no indication, at the scale they could measure, that the drift was tapering off towards some nearby source. Here is the logical chain Kashlinsky was forced to follow. Every known gravitational source within the observable universe had been mapped and accounted for. The distribution of matter, the clustering of galaxies, the superclusters and filaments of the cosmic web. All of it was included in the calculation. None of it explained the drift. The clusters were moving toward a point that, by every accounting of what lies in that direction within the observable universe, had no source. The pull was coming from outside the survey, from outside everything. Picture a room where every piece of furniture is slowly sliding toward one wall. You check the wall, solid, no magnets, no openings. You check the floor, level, no slope. You check the air, no obvious pressure differential. The movement continues regardless. Now picture the room as the observable universe. Every large structure you can see, every galaxy cluster across the sky, drifting consistently towards something that does not appear on any map of what exists inside the room. Kashlinsky was not imagining the movement. His measurement technique had been independently validated. The signal was in the data, and it was persistent across every extension of the survey he performed. The drift did not diminish as the survey grew larger. A local source would produce a drift that tapered off with distance. This one did not. It behaved like a pull from something far beyond the survey's edge. So the clusters are drifting, hundreds of them, across 2.5 billion light-years, all moving at 2 million miles per hour toward the same point. Every gravitational source within the observable universe has been accounted for. The internal accounting does not balance. There is motion with no known cause, which means the cause is somewhere the accounting does not reach. The observable universe is not everything that exists. It is the sphere of space large enough for light to have reached us since the Big Bang, a region roughly 46 billion light-years in radius. Everything beyond that boundary has been carried away by the expansion of space at a rate faster than light can close the distance. Their light will never arrive. Their gravity, however, is a different matter. Gravity propagates through space-time, and a gravitational influence established during the inflationary epoch, before the expansion snapped the horizon shut, could persist as a pull felt by everything inside the boundary. Kashlinsky proposed this explicitly. In his papers and in subsequent interviews, he described the source of dark flow as likely a massive concentration of matter or energy that formed in the same inflationary epoch as our universe, expanded beyond our horizon over the 13 billion years since, and is now inaccessible to every instrument we possess, readable only through the gravitational tug it exerts on the visible matter inside our universe. Think about what that implies. Our universe is not drifting freely through empty space. It is being pulled, something we cannot see, cannot reach and cannot detect directly is exerting a gravitational force large enough to move hundreds of billions of galaxy clusters at 2 million miles per hour across a region 2.5 billion light-years across. And this pull has a direction. The direction is south. Before we move forward, I want to clarify what beyond the observable horizon actually means in this context, because it is easy to hear the phrase and think it means merely very far away. It does not. The observable horizon is not a distance limitation that better technology could eventually overcome. It is a fundamental boundary set by the finite age of the universe and the finite speed of light. Since the Big Bang, the universe has existed for roughly 13.8 billion years. Light can travel at most that many light-years in that time. Everything farther than about 46 billion light-years away, accounting for expansion, has been receding from us faster than light can close the gap. Whatever is pulling the clusters is in that permanently inaccessible region. We cannot point a better telescope at it. We cannot design an instrument to detect it directly. The only evidence it will ever leave us is the motion of the matter it is pulling from inside our boundary. The motion Kashlinsky measured. The question of whether that measurement is correct is still open. What is settled is the implication if it is. 2 years before Kashlinsky published his dark flow results, a physicist named Laura Mersini Houghton at the University of North Carolina at Chapel Hill was working from string theory and the mathematics of multiple universes. Working with her collaborator Richard Holman at Carnegie Mellon University, she built a theoretical framework for how a universe forming inside a larger, inflating space, not alone, but surrounded by other bubble universes nucleating in the same process, would show evidence of those neighbors. The two published their results in 2006 and 2007. The predictions were specific. If our universe formed as a bubble alongside other bubble universes, and if those neighboring universes interacted gravitationally and quantum mechanically with ours during the inflationary epoch, 2 measurable signatures would remain in the CMB. First, a cold region in the southern sky, where the gravitational and quantum mechanical repulsion from a neighboring universe had suppressed structure formation on that side of our forming cosmos. Second, a coherent drift of matter toward the gravitational shadow of that same neighbor's mass beyond our horizon, a bulk flow of galaxy clusters moving in the direction of the source's center of gravity. These were not vague qualitative predictions. They specified the type of signature, the general region of sky, and the physical mechanism that would produce each one. Mersini Houghton submitted this work before the cold spot analysis was complete. Before Kashlinsky's dark flow paper existed, she was working from equations about universes she had never observed, predicting marks she had never seen in data she had not yet accessed. Here is why predictive power matters above almost everything else in science. After the fact, almost any theory can be adjusted to fit existing data, add parameters, tweak constants, propose additional mechanisms until your framework reproduces the pattern you observe. This is how many cosmological models work. Mersini Houghton did the opposite. She built a framework from first principles, committed its predictions explicitly to the scientific record, and submitted them before the evidence arrived. This is the highest standard of scientific validation, not explaining what you already see, but specifying what you will see before you look. When Kashlinsky published in 2008, her predictions were already in the literature. When Planck confirmed the cold spot in 2013, her predictions were already in the literature. She did not need to retrofit anything. Her equations pointed at a map she had never seen and said, there will be something cold in the south, and the clusters will be drifting towards something beyond the boundary. People looked. The cold thing was there. The clusters were drifting. You can construct a theory to fit existing data and prove nothing. You cannot fake a prediction made before the data was collected. The question her predictions force onto the table is not whether she was lucky. The question is whether her framework is correct. Because if it is correct, the reason it is correct matters enormously. The reason is built into every equation of her framework, Our universe formed alongside others. Those others were close enough to touch. Mercini Houghton wrote in her 2007 paper, co-authored with Holman, "If we live in a landscape of vacua, the formation of our universe was not an isolated event. It was embedded in a larger quantum context, and that context leaves traces." That is the careful, measured language of a physicist publishing in a peer-reviewed journal. The non-careful version, the version that follows the logic to where it actually leads, is this. Our universe was born next to other universes. They pressed against it while it was still forming, and the scars of that contact are encoded in the oldest light we can see. Mercini Houghton identified what those scars would look like before anyone had mapped them with sufficient precision to confirm they were there. Then the maps improved. The scars were there. You are probably thinking, 2 predictions matching the data is impressive, but predictive agreement is not the same as proof. One physicist getting 2 qualitative predictions right could still be an extraordinary coincidence. Fair. That objection deserves a direct answer. In science, proof is not binary. It is a weight of evidence that accumulates until the probability of the alternative becomes untenable. Consider the full sequence. In 2006 and 2007, Mercini Houghton and Holman published their framework with explicit predictions: a cold region in the southern CMB sky, and a coherent bulk drift of galaxy clusters toward a gravitational source beyond the horizon. These are the predictions. In 2008, Kashlinsky publishes the dark flow results: hundreds of galaxy clusters moving at 2 million miles per hour toward the south, with no known internal source. In 2013, Planck confirms the cold spot at high statistical confidence. The direction of both matches the equations Mercini Houghton had written years earlier. In science, there are 2 ways to explain this. First, coincidence. Her framework happened to produce the right qualitative predictions, despite being built on false premises, and the actual physical causes of both phenomena are something else entirely that happens to align with what she said. Second, the framework contains something true about how the universe actually works. Both options remain open. What is not open is the claim that her work is unimportant. Predictive power before observation is the rarest and most valuable commodity in theoretical physics. Mercini Houghton's framework has it. What does her framework require? It requires that our universe formed as a bubble in a larger inflating space, alongside other bubble universes nucleating in the same process. It requires that during the earliest moments of formation, before our universe expanded into the shape it now holds, neighboring universes were close enough to leave gravitational and quantum mechanical imprints. The cold region is the imprint of repulsion from a neighbor. The dark flow is the imprint of a neighbor's gravitational mass, pulling from just beyond what we can see. Both signatures are in the oldest light we can access and in the large-scale motion of massive structure across the sky. Other universes, in her framework, are not a philosophical abstraction. They are physical objects. They were close enough to our forming universe to press against it. They left marks. We have instruments that can read those marks. We have a physicist who predicted them before they were confirmed. If she is right for the right reasons, those marks in the CMB are the only messages we will ever receive from something that exists outside everything we can observe. We are not finished reading them. The cold spot she predicted is confirmed. The dark flow she predicted is a live scientific question. Both are in the direction her equations specified. Her framework, built from string theory and multiverse mathematics, generated these predictions from a set of physical assumptions: that our universe is not alone, that it formed in proximity to other forming universes, and that those universes interacted with ours during inflation. If those assumptions are wrong, she got lucky in a way that exceeds any reasonable probability. If those assumptions are right, the implications run much deeper than 2 CMB anomalies. They restructure everything we think we know about what kind of thing our universe is. The process that made you possible has never stopped. To understand what Mercini Houghton's framework is built on, you need to understand the mechanism that produces multiple universes in the first place. Standard inflationary cosmology says our universe underwent explosive expansion in the first tiny fraction of a second after the Big Bang, driven by a quantum field called the inflaton. This field was in a high-energy state, and its energy drove space to expand so violently that in a time smaller than any interval we have a name for, the region that would become the observable universe grew from something smaller than an atom to something larger than a galaxy. Then the inflaton field decayed, its energy converting into matter and radiation. Inflation ended. The universe we know began. That is the version in every textbook. Here is what physicists Andrei Linde at Stanford and Alexander Vilenkin at Tufts discovered in the 1980s, working independently from each other. Inflation cannot stop everywhere at once. The same quantum mechanics that drives inflation also introduces random fluctuations in the inflaton field at every point in space. In most regions, those fluctuations cause the field to decay, ending inflation locally and producing a pocket universe like ours. But in other regions, the fluctuations push the field back up to higher energy before it can decay. Those regions continue to inflate. They expand faster than light, growing without bound, perpetually driven by the same inflaton energy that eventually ended in our region. You are probably thinking, fine, but this is all mathematics. Having 10 to the power of 500 possible universes is meaningless if we can only ever observe one of them. This objection is fair. Here is the answer. The landscape is the menu. Eternal inflation is the mechanism that samples it. Every pocket universe, nucleating in the eternally inflating space, lands at a different point in the landscape and emerges with different physics. Our universe's configuration, our specific particle masses and constants, is one entry on a menu of staggering size, and the process generating entries has never stopped. The machine is still sampling, the menu is still open, and the universes nucleating right now in that inflating space occupy every possible configuration, including those where the ground state of reality is lower than ours. That last detail is where the investigation turns. The eternal inflation framework produces an infinite sequence of bubble universes. Understanding what happens when those bubbles form near each other requires working through the geometry, because the geometry is where the evidence lives. Each bubble nucleates at a point in the eternally inflating space. The moment it forms, it begins expanding. The inflaton field within the bubble decays. Matter and radiation fill the new space, and the bubble grows at a rate approaching the speed of light. Meanwhile, the inflating space surrounding the bubble also expands exponentially. Two competing processes: bubble growth and the growth of the gaps between bubbles. For most pairs of universes, the gap wins. The inflation between them carries them permanently out of contact before their walls ever touch. But for universes that nucleate close enough together, within the same patch of inflating space, before the exponential growth has opened a permanent gap, the geometry is different. Two closely nucleating bubbles can collide. When the expanding walls meet, energy is released at the contact surface, and a distinct imprint propagates into the interior of each bubble. In our universe, that imprint would appear in the CMB as a disc-shaped temperature anomaly with a specific geometric profile, roughly circular, sharper at its edges than a random CMB fluctuation, with a temperature pattern following a predictable mathematical form. Massini, Houghton, and Holman worked out the collision signatures in their 2007 paper, but the broader physics of bubble collisions was treated independently and rigorously. Physicists Anthony Aguirre at the University of California, Santa Cruz, and Matthew Johnson at the Perimeter Institute published a detailed treatment in 2010 specifying what a CMB sky containing bubble collision scars would look like. Circular, a temperature profile following a particular mathematical form. Polarization signatures differing from random fluctuations in a measurable and specific way. The analogy worth building here is physical: two soap bubbles expanding in a small container. If they form far apart, one pops, and the other grows into the freed space. If they form close enough that their walls meet before the container can separate them, the surfaces touch and both bubbles carry the contact geometry. The ring where they meet has a shape completely predictable from surface tension and bubble sizes. A physicist who knew the surface tension equations could calculate the ring's shape before ever seeing it. Universe collisions work the same way. The physics of how expanding regions of space interact when their walls meet is mathematically well defined. Aguirre and Johnson ran the calculation. The result is a circular imprint with specific geometric properties, distinct enough from background fluctuations that a systematic search could separate them from noise. Here is the chain link that matters. Mersini-Houghton predicted a cold region in the southern sky from quantum mechanical repulsion between neighboring universes. The collision physics, developed independently by a different team using different methods, predicts circular disc-shaped scars. These are two distinct signatures of the same underlying event, the formation of our universe in proximity to another. If the first signature exists, the second should be nearby. The southern sky that carries one kind of multiverse mark should carry both. The cold spot had been confirmed at high statistical confidence by 3 independent satellite missions. If bubble collision physics was correct, circular scars should be in that same region of sky. The theoretical framework was specific enough, the prediction was geometric enough, that a rigorous search was now possible. Some physicists decided to build the tool and look. In 2011, 3 physicists published a paper that deserves more attention than it received. Stephen Feeney at University College London, Matt Johnson at the Perimeter Institute for Theoretical Physics, and Daniel Mortlock at Imperial College London built a Bayesian statistical framework specifically designed to search CMB data for the signatures of bubble universe collisions. This was not a repurposed tool. It was designed from the ground up for this one purpose. They built it because the theoretical prediction was specific enough to search for, and the prediction had passed enough preliminary tests to justify the effort. The Bayesian approach is the right tool for this problem. Standard statistical tests search for signals against background noise and return a probability the signal is real. Bayesian analysis does something more powerful. It takes the theoretical prediction, the specific form and geometry of the expected signal, and asks how much more likely the actual data is if the signal is present compared to if it is absent. This ratio is called the Bayes factor. A Bayes factor of 100 means the data strongly favors the signal hypothesis over the null. Feeney and collaborators applied this framework to the full WMAP dataset. Building this tool was itself a statement. In science, instrument construction is a vote. Particle physicists built 27 kilometers of superconducting magnets at CERN because the theoretical predictions for the Higgs boson were specific enough to warrant the search. Radio astronomers designed specific receiver configurations for narrowband signal searches because the theoretical case was developed enough to know what shape to listen for. You build the tool when you believe the prediction is real enough to test. The physics community's decision to fund and publish a systematic bubble collision search means the theoretical case had crossed a threshold. Feeney, Johnson, and Mortlock were careful about their claims. They were running a search, not a discovery paper. Their framework would either find candidate signals and quantify the statistical case for them, or it would rule them out to the precision of the available data. A rigorous null result is as informative as a detection when the search is properly designed. The framework searched for circular temperature anomalies with the specific profile predicted by collision physics. The search did not look for cold spots generically, or for any circular feature. It looked for features whose shape matched the mathematical form that arises specifically when the edge of one expanding universe passes through the interior of another. The WMAP data was the best full-sky CMB map available in 2011. Planck had not yet released its higher resolution data. Feeney and collaborators ran their full Bayesian framework across the entire sky recording every candidate location where the data preferred the bubble collision model over the null hypothesis. They found something. The fact that this paper appeared in Physical Review Letters, one of the most selective physics journals in the world, means the methodology was peer-reviewed and found sound before anyone could evaluate whether the results were convenient. The search was valid. What the valid search found is the next chapter. But the significance of the search itself needs to register. The physics community built a specific instrument for a specific prediction made by a theoretical framework that had already passed 2 observational tests. That sequence of events is what scientific investigation looks like when it is working. Feeney, Johnson, and Mortlock ran their Bayesian bubble collision search across the full WMAP sky. The framework returned 4 candidate signals. Every one of them was in the southern hemisphere of the CMB. The Bayes factor for each candidate was approximately 2-to-1 in favor of the collision hypothesis over random fluctuation. 2-to-1 is not a discovery. The standard physics uses to call something confirmed is 5 sigma confidence, corresponding to a probability below 1 in 3.5 million that the result is a random fluctuation. 2-to-1 is roughly where you stand after flipping a coin twice and getting the same result. Interesting, worth pursuing, not conclusive. Feeney and collaborators were explicit about this. Their paper called the results consistent with bubble collision signatures and called for more sensitive data. They did not claim discovery. They reported a direction. The detail that changes everything is not the Bayes factor, it is the location. 4 candidates, 4 results from a blind analysis of the full sky, meaning the algorithm was not told to look in the south. It searched the entire sky equally and returned 4 results. All 4 were in the southern hemisphere. More specifically, all 4 were in the same region of the southern hemisphere, where the cold spot, the hemisphere asymmetry, the axis of evil, and the dark flow had all independently pointed. Work through the probability explicitly. If bubble collision signatures were distributed randomly across the sky, and if 4 candidates emerged from the search, the probability that all 4 would fall in the same hemisphere by chance is 1 in 16. That sounds like still plausible coincidence. But these 4 candidates did not land anywhere in the southern hemisphere. They landed in the same specific region of the southern hemisphere as every other anomaly in this investigation, a region that had already accumulated 4 independent lines of anomalous evidence from 4 independent teams using 4 independent methods. The pattern was now 5 measurements deep. Feeney and collaborators were not multiverse advocates publishing to advance a preferred theory. Their paper was methodological. Here is a rigorous tool. Here is what the tool found. Here is the statistical weight. Here is what better data would resolve. They disclosed every limitation. The WMAP data resolution was insufficient to confirm or rule out the bubble collision profile at the precision needed for a discovery claim. That would require Planck. Planck's first full-sky data release was 2013. The Planck collaboration did perform a bubble collision search using higher resolution data. The results were published in their subsequent papers. The outcome, consistent with the theoretical prediction, below the threshold for a discovery claim in the southern hemisphere. The pattern held under the improved instrument. It neither broke nor confirmed. It persisted. 5 independent datasets. The cold spot from temperature analysis, the hemisphere asymmetry from power spectrum analysis, the axis of evil from multipole alignment analysis, the dark flow from kinematic analysis of galaxy clusters, the bubble collision candidates from Bayesian geometric analysis. Different instruments, different teams, different mathematical frameworks, different data types, different decades. The answer keeps coming back the same direction. Every time the measurement improves, the same region of sky looks back. At this point in the investigation, I want to do the explicit accounting because the accumulated weight of what we have found is the argument itself. 5 lines of evidence. Each was discovered separately. Each was found by a different team working on a different question with a different tool. Here is what each requires. The cold spot. 3 to 5 standard deviations below prediction in the southern sky, confirmed by WMAP and Planck across a decade, with the supervoid explanation covering at most 20% of the effect after Ruari-Mackenzie's 2017 analysis. The remaining 80% requires either unknown physics within the standard model or a process that acted on our universe from outside it. The hemisphere asymmetry. The entire southern half of the CMB sky carries more large-scale structure than the northern half, at odds of roughly 1 in 10,000 against a random origin, confirmed independently by WMAP and Planck with different analysis pipelines. No agreed-upon explanation within the standard model. The axis of evil, the two largest features in the observable universe, are aligned along a common axis, pointing toward the southern ecliptic, at odds of roughly 1 in 1,000 against random alignment, confirmed by Planck using independent instruments from WMAP. The dark flow, hundreds of galaxy clusters across 2.5 billion light-years, are moving toward the south at 2 million miles per hour, with no known gravitational source within the observable universe. Kashlinski's analysis requires an attractor beyond the cosmic horizon. The bubble collision candidates. 4 results from a blind Bayesian search of the full CMB sky, all in the southern hemisphere, all in the same region as every other anomaly, consistent with the theoretical profile predicted for bubble universe collisions. 5 independent datasets, 5 times the same direction. The probability of this occurring by coincidence compounds with each additional alignment, 1 in several 100,000, times 1 in 10,000, times 1 in 1,000, times an unresolved kinematic anomaly, times a geometric clustering in one hemisphere. The product is a number so small that coincidence has become the least parsimonious explanation available. Here is the objection the careful skeptic raises right now. Each of these anomalies is individually marginal. The bubble collision candidates are nowhere near discovery threshold. The dark flow debate is scientifically unresolved. The cold spot might still be a rare statistical fluctuation. The hemisphere asymmetry and axis of evil are confirmed but not proven to require an exterior cause. Everything remains uncertain. This objection is technically correct. Nothing on this list is individually confirmed at a level that would support a definitive causal claim, but the objection applies to each piece alone, not to the pattern they form together. 5 anomalies, independently measured, all pointing the same direction, is not 5 uncertain data points. It is one signal read through 5 independent instruments. The pattern is the evidence. The convergence is what demands an explanation. Something in the southern sky, or beyond the southern edge of our observable universe, has organized itself into 5 independent measurements by 5 independent teams across 3 independent satellite missions and decades of observation. The measurements did not plan to agree. They just did. The direction is real. What sits at the end of it is what we cannot yet see. The pattern in the CMB is one problem. The next problem is larger in scope and was discovered by accident. In 1998, 2 independent teams of astronomers were racing to settle a basic question. How fast was the universe's expansion decelerating? Gravity should be pulling everything together, slowing the outward flight of galaxies over time. The competition was to measure the deceleration rate precisely. Both teams used Type Ia supernova explosions as their measuring tool. These explosions have a characteristic peak brightness that allows astronomers to calculate exact distances even across billions of light-years of space. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at Australian National University and Adam Rees at Johns Hopkins University, reported their results within months of each other. The universe was accelerating. Every distant supernova was further away than a decelerating universe would place it. Every distant galaxy was receding faster than any model of gravitational deceleration predicted. Both teams had checked every systematic error that could mimic this result. The answer held across every reanalysis. Something was pushing all of space apart with increasing force over time, and that something accounted for approximately 68% of all the energy in the universe. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The name given to the cause was dark energy. That name is not a description, it is a label placed on a complete absence of understanding. Dark energy fills all of space. As space expands and new volume is created, dark energy does not dilute the way ordinary matter or radiation dilutes when the volume containing it grows. Its density per unit volume stays constant, which means the total amount of dark energy in the universe grows as the universe grows. Dark energy is generating energy as the universe expands, with no identified source for that energy within any known physics. It simply accumulates with the volume of space, from nothing we can point to. Consider the proportions. Dark energy is approximately 68% of the universe's total energy budget. Dark matter, the gravitationally active but otherwise undetectable substance that holds galaxies together, is approximately 27%. Every star, every planet, every atom of ordinary matter, every photon of light, everything humanity has ever detected or described in the 400 years since Galileo pointed a telescope at the sky, constitutes approximately 5%. The dominant component of reality was discovered by accident and has no explanation. This connects to the CMB anomalies through the next step in the chain. Dark energy fills space uniformly. It is isotropic. It cannot, on its own, explain why the southern sky is anomalous. But dark energy's existence, and more specifically the precise value of its energy density, requires an explanation that cannot come from within the observable universe. The value is extraordinarily small by the standards of quantum field theory. Finding out why it is that specific small value, rather than zero or something vastly larger, has consumed theoretical physics for decades. That explanation leads where everything else in this investigation leads. Perlmutter, in interviews after the Nobel announcement, described the discovery as the biggest unsolved problem in physics. The universe is 68%, something we cannot explain, generating energy from no source we can identify. And the reason it has, the precise value it has, is something the universe we can see cannot tell us. Quantum field theory is the most precisely tested scientific framework in history. It describes fundamental particles and fields with accuracy that, in some cases, matches experimental measurements to more than 10 decimal places. It underlies every calculation in particle physics. It has never failed a precise laboratory test. Quantum field theory also predicts that empty space is not empty. Even in the total absence of particles, quantum fields fluctuate. Virtual particle-antiparticle pairs pop into existence and annihilate almost instantly, but they carry real energy during their brief presence. This is called vacuum energy, and it is confirmed in other contexts. The Casimir effect, the tiny attractive force between two uncharged metal plates placed very close together in a vacuum, arises directly from vacuum energy fluctuations between the plates, and has been measured precisely in laboratory experiments. The Lamb shift, a tiny splitting in the energy levels of hydrogen atoms, is another experimental confirmation of vacuum energy. These are real, measured phenomena. The vacuum energy is real. When physicists calculate the vacuum energy density that quantum field theory predicts for empty space, and compare it to the dark energy density measured from supernova surveys and the CMB, the two numbers disagree by a factor of 10 to the power of 120. That exponent is not a typo or an approximation. It is the result of the calculation. The predicted vacuum energy density is 1 followed by 119 zeros times larger than what we observe. Nobel laureate Steven Weinberg called this the cosmological constant problem in his landmark 1989 review paper, and described the situation directly. Either the quantum field theory calculation is catastrophically wrong at cosmological scales, or something is cancelling nearly all of the predicted vacuum energy with extraordinary precision, leaving only the tiny residue we observe as dark energy. Here is the chain that matters. If the vacuum energy is being cancelled, something is doing the cancelling. The precision required is the most extraordinary fine-tuning in all of physics. The cancellation must reduce the theoretical prediction by a factor of 10 to the power of 120, leaving just enough residual energy density to match what we measure. No mechanism within the standard model of particle physics achieves this. No mechanism within general relativity achieves this. The answer has to come from somewhere outside both frameworks. The string landscape is the only serious proposal that addresses this without invoking unexplained fine-tuning. In the landscape, the vacuum energy of each pocket universe is different. Most configurations carry a vacuum energy so large that the universe either collapses immediately or expands too fast for structure to form. Only a tiny fraction of configurations carry a vacuum energy small enough to permit galaxies. We inhabit one of those rare configurations because the others produce no observers. This is called the anthropic solution, first formalized by Weinberg in the same 1989 paper. Weinberg went further. If the anthropic selection is doing the work, he predicted that the cosmological constant should be small, but not zero, just large enough to be detectable, but small enough to permit structure. In 1998, Perlmutter, Schmidt, and Rees confirmed dark energy exists. It is small. It is not zero. Weinberg's prediction matched the data. His prediction required the landscape. The landscape requires the multiverse. The multiverse requires eternal inflation. Eternal inflation is the same mechanism that, in Mersini-Houghton's framework, produced the bubble collision that left a bruise in our southern sky. The largest mismatch in the history of science has only one surviving explanation. That explanation is the same explanation the CMB anomalies point toward. Every door in this building leads to the same hallway. The Hubble constant is the number describing how fast the universe is currently expanding. Getting it right matters because every cosmological distance, age, and evolution calculation depends on it. Two fundamentally different measurements exist. The first is the early universe approach. Analyze the CMB, fit the standard model to the data, and infer the expansion rate that must have been present at the moment when the plasma fog lifted to produce the CMB pattern we observe. The Planck satellite completed this measurement in 2018 with extraordinary precision. The answer: for every 3.3 million light-years of distance between two objects, the expansion adds 67.4 kilometers per second to their recession speed. The second is local measurement. Build a distance ladder using Cepheid variable stars to calibrate nearby galaxy distances. Use those calibrations to measure recession velocities at various distances and extract the expansion rate directly from current observations. This method was refined across decades, substantially by Adam Rees and collaborators. Their answer, confirmed and refined through multiple publications into the 2020s, 73 kilometers per second for the same unit of distance, roughly 9% faster than the CMB-derived value. A 9% gap separates the two answers. The gap does not close with higher precision. It becomes more significant as error bars shrink. Each refinement confirms the two measurements are genuinely inconsistent at statistical confidence, now exceeding 5 standard deviations. In 2023, the James Webb Space Telescope repeated the local distance ladder measurement with greater precision than the Hubble Space Telescope had achieved. The result confirmed the higher local value and definitively ruled out instrumental error as the cause of the discrepancy. The Hubble tension survived the most rigorous test ever applied to it. 5 standard deviations is the threshold physics uses to call something real. The Higgs boson was announced as discovered at CERN when the confidence reached 5 sigma in 2012. The Hubble tension is at 5 sigma. The two measurements disagree in a way that is confirmed at the level that physics uses for confirmed discoveries. Here is the chain. The standard model of cosmology cannot satisfy both measurements simultaneously. Set the model's parameters to match the CMB, and the local expansion rate comes out too low. Set them to match the local measurement, and the CMB prediction disagrees with what Planck actually observed. The same universe, measured at two different epochs using two independent methods, returns two answers that cannot coexist within the current theoretical framework. The leading explanations among the theorists who work this problem require something not in the standard model: an early dark energy component, new interactions in the pre-recombination era, a transition in vacuum energy during the universe's history. Every resolution with the right magnitude to close the gap invokes physics from outside the current framework. Several of the most developed proposals require new vacuum physics or landscape-level mechanisms. The early universe and the present universe disagree about how fast reality is moving. Between those two epochs, something happened that the model of an isolated, self-contained universe cannot accommodate. The standard model cannot fix itself using only the contents of the observable universe. Something happened in between that we do not have. 4 observational anomalies: the cold spot, the hemisphere asymmetry, the axis of evil, the dark flow, each confirmed by independent instruments over 2 decades, each pointing outside the standard model. Dark energy, the cosmological constant problem, the Hubble tension. 3 theoretical and observational failures of the standard model. Problems where the best available framework either produces a number that is off by a factor of 10 to the power of 120, or gives 2 inconsistent answers for the same quantity. I want to do something direct here. I want to follow every proposed solution that has survived serious mathematical scrutiny for any of these problems and show where each one leads. For the cold spot, the supervoid covers 20% of the anomaly. The remaining 80% has resisted every proposal within the standard model. The candidates that survive require either new inflationary physics or an effect from beyond the observable horizon. Mersini-Houghton's multiverse framework predicts both the cold spot's location and its magnitude from first principles. For the cosmological constant problem, the only calculation-based approach that reproduces the observed dark energy value without requiring extraordinary fine-tuning is the anthropic selection in the string landscape, requiring a vast ensemble of universes with different vacuum energies. Weinberg formalized this in 1989. The discovery of dark energy in 1998 confirmed his prediction. For the Hubble tension, every resolution that accounts for both measurements requires new physics before recombination, or a vacuum energy transition, or landscape-level mechanisms. The standard model's internal resources are insufficient. An outside ingredient is required. For the bubble collision candidates, if real, they require 2 universes to have been close enough at the moment of our formation to leave geometric scars on our CMB. This requires the eternal inflation framework. The eternal inflation framework requires the landscape. Here is my position on what the pattern is saying. These are not unrelated problems that happen to aim at the same direction. They are different instruments measuring the same underlying reality. A reality in which the observable universe is one component of a larger system, where the vacuum we inhabit is one of many possible configurations, where the physics we experience is locally specific rather than universally fixed, and where the formation of our universe was not an isolated event. The analogy worth thinking through: imagine 7 different pressure gauges placed around a sealed room, designed by different engineers working in different decades using different measurement principles. Every gauge reads the same anomalous pressure. You could argue that each gauge individually might be miscalibrated. You cannot argue that all 7 are wrong in the same direction at the same time by coincidence. At some point, the reading is the result. The room has a leak. Every door that cosmologists have tried to open in 30 years of pushing on the standard model's failures leads to the same hallway. The hallway exists beyond the edge of everything we can observe, and the hallway is not the problem. The hallway is the answer. The universe cannot explain itself. Every attempt to explain it from the inside runs into a wall. The wall is where the outside begins. On the 4th of July, 2012, scientists at CERN confirmed the existence of the Higgs boson. The announcement reached the physics community as a triumph. The last missing piece of the standard model of particle physics, the particle that completes the framework, had been found. Its mass was measured at approximately 125 billion electron volts. The measurement was clean. For most of the physicists in the room that day, it was the end of a 50-year search. For a smaller group of theorists who had been watching the Higgs mass measurement approach, it was the beginning of something else entirely. The Higgs boson is the excitation of the Higgs field, a quantum field that permeates all of space and gives fundamental particles their mass. Electrons, quarks, the particles that build every atom in your body, they acquire mass by interacting with the Higgs field as they move through it. The Higgs field sits at a specific value, determined by the minimum of its potential energy, the shape of the energy landscape it occupies. A field at the minimum of its potential is in its lowest available energy state. That is a stable configuration. A field sitting in a local minimum that is not the global lowest point is in a metastable state, stable for long periods, but sitting in a pocket, not on the floor. In 2012 and 2013, theoretical physicists Donald Butazzo and collaborators at the University of Milan published calculations of the Higgs field's potential using the confirmed Higgs mass and the top quark mass of approximately 173 billion electron volts. These two numbers feed into renormalization group equations that trace how the Higgs potential behaves at energy scales far beyond any particle collider. The calculations are standard, well understood physics. Butazzo's team ran them. The Higgs potential dips below zero at very high energy scales, around energies of 10 to the power of 10 billion electron volts, well beyond collider reach but within the mathematical domain of the equations. The potential becomes negative. A negative potential means the current vacuum state is not the true ground state. There is a lower configuration. The true minimum of the Higgs field exists at some value the field has not yet reached. Between us and that minimum is a potential barrier. The current vacuum of the Higgs field sits on one side of that barrier. The true ground state sits on the other. Think about what this means physically. A ball resting in a shallow bowl partway up a hillside. The bowl holds the ball against small perturbations. Push the ball gently. It rolls back to the center. The ball is stable, but there is a deeper valley at the base of the hill. Climb the rim of the bowl, and the ball rolls permanently to the lower valley. The bowl is not the floor. The floor is elsewhere. Butazzo and colleagues calculated the stability phase diagram for the Higgs vacuum using the best available particle masses. Their 2013 result placed our vacuum in the metastable zone, the region physicists call false vacuum, by a statistically real margin. Subsequent analyses with more precise particle mass measurements have refined the calculation repeatedly. The consensus, as of the most recent analyses, places the current vacuum in the metastable region with high confidence. The field that gives your protons and electrons their masses, that holds every atom in your body in its current form, is sitting in a shallow pocket of an energy landscape that has a lower floor. The floor is reachable. The pocket is stable for now. For now is doing a great deal of work in that sentence, and the next chapter is why. Vacuum decay proceeds through a specific mechanism, and the mechanism has an implication that needs to be walked through step by step because it does not announce itself. A quantum field can tunnel through a potential barrier the way a quantum particle tunnels through a physical wall. This is experimentally confirmed physics. It underlies the function of transistors in every device containing electronics and nuclear fusion in every star. For a quantum field that fills all of space, tunneling does not happen everywhere simultaneously. It happens at one point in space. At some location, a quantum fluctuation in the Higgs field crosses the potential barrier and transitions to the true ground state. A bubble forms where the Higgs field carries a different value, where particles may have different masses or cease to exist in their current forms. The bubble has a wall, a thin boundary where the transition lives. The wall expands. The true vacuum is more energetically favorable than the false vacuum surrounding it. The physics drives the wall outward. Quickly, the wall reaches the speed of light. As it passes through any region of space, the molecules, atoms, and electromagnetic forces in that region all depend on the Higgs field in its current configuration. As the wall passes, the configuration changes. What the wall leaves behind is space operating under different rules. Whether any configuration capable of experience could survive inside a true vacuum region is a question physics cannot currently answer, because the physics inside that region is different from the physics we use to reason about it. The same conclusion holds for any civilization, anywhere in the universe. A civilization with instruments 1,000,000 years more advanced than ours, spread across 1 billion star systems, with sensors of every kind we can imagine and many we cannot, has the same warning time as anyone. 0. The limit is physics. Eric Weinberg at Columbia University, who has done foundational work on the mathematics of bubble nucleation, describes the expanding bubble wall as a literal event horizon. Nothing from beyond it has reached you yet, and the moment it reaches you is the moment you are inside it. The horizon and the event are not separate things. They are the same thing. The category of existential threat that has a detection window of 0 is a different kind of threat from everything else we reason about. Asteroid impacts, nearby stellar explosions, even a gamma-ray burst from a close star. We can model timescales, build detection networks, at least in principle prepare. Vacuum decay sits in a separate category, physically undetectable by anyone, anywhere, at any level of technological sophistication. Because of the speed at which both the threat and the information about it travel, there is an entire class of event the universe can produce that is invisible by definition. That knowledge does not expand your options. It gives you a clearer picture of how little control any of this affords. Here is a connection that the research literature approaches carefully and then generally moves away from. The theoretical framework that Massini-Houghton invokes to explain the cold spot is eternal inflation in the string landscape. Multiple bubble universes form in that eternally inflating space, each nucleating at a specific position on the landscape, each emerging with different physical constants, different particle masses, different vacuum energies. Our universe sits at a particular landscape position, the metastable configuration that the Higgs field calculations have established with high confidence. Extend the picture one step, the neighbors that our universe formed alongside, the bubble universes that pressed against ours during the inflationary epoch and left a mark on the southern sky, also nucleated at specific landscape positions. Each position is different from ours. Some of those universes may sit closer to the true ground state of the landscape than we do. Some may occupy stable vacuum configurations while we occupy a metastable one. The interaction that left the cold spot was an interaction between our forming universe and one of those neighbors. The question the research literature does not resolve is what kind of neighbor it was. If it nucleated at a landscape position closer to the true vacuum than ours, then the interaction at the boundary was between a metastable region and a configuration closer to the ground state. The physics of what happens at such a boundary has a specific shape, a region of lower vacuum energy pressing into a region of higher vacuum energy, with the lower energy configuration tending to expand into the metastable space. That is exactly the shape of vacuum decay propagation. The cold spot may be the echo of an event at the boundary between our universe and a dimmed neighbor with a lower floor. The suppression of structure formation in the southern sky, in the region that faced the interaction, would be a record of what that boundary contact did to our universe while it was still forming, still soft enough that pressure from outside could leave a permanent imprint in the density fluctuations that eventually became the CMB temperature pattern. The scar in the southern sky and the ledge our physics sits on may be evidence of the same event viewed from different angles. The CMB carries the geometric memory of the interaction. The Higgs field carries the consequence. A universe that formed near a lower vacuum neighbor emerged at a specific position on the landscape, a metastable position because the neighbor's occupying configurations closer to the ground state had already pressed against us during formation. I want to be precise about the epistemic status of this connection. Mersini-Houghton's framework predicts the cold spot's location and magnitude from multiverse mathematics, and those predictions were made before the measurements they predicted. That is an established fact about the theory's predictive record. The Higgs metastability is established physics, confirmed by particle mass measurements from CERN. The direct claim that the same multiverse interaction caused both observations is a theoretical inference. It follows from combining the two established results within the same landscape framework, but it has not been confirmed independently. What has been confirmed is this: the framework that explains the cold spot and the framework that explains the Higgs metastability are the same framework. The string landscape is the mathematical structure underlying both. If the landscape is real, and the CMB predictions give us reason to take that seriously, then the cold spot and the ledge we are sitting on are entries in the same ledger, two separate problems in physics, one possible cause. I want to stop the science for a moment. I want to tell you exactly what you are sitting inside right now, and I want to be completely direct about it. The universe you inhabit is asymmetric. Its oldest light is wrong in 5 distinct ways, all pointing in the same direction on the sky, confirmed by 2 independent satellite missions across more than 2 decades. The southern half of the sky carries more large-scale structure than the northern half, by a margin that rules out a random origin at odds of 1 in 10,000. 2 of the universe's largest coherent features are aligned along a common axis, pointing toward the southern ecliptic, at odds of 1 in 1,000 against random alignment. A region of the oldest light, spanning a volume 1.8 billion light-years across, is colder than any standard model simulation has ever produced, and the one credible mundane explanation covers only 20% of the effect. Hundreds of billions of galaxy clusters are drifting toward a gravitational source that does not exist within anything we can observe. The dominant component of the universe's energy budget has no explanation within physics, as currently understood. The energy accelerating the expansion of all space is generating itself as the universe grows, from no identified source. The quantum field that gives every particle its mass, that makes atoms possible, that makes you possible, sits in a metastable configuration rather than the true ground state of the energy landscape. The early universe and the present universe disagree about how fast reality is moving by a margin confirmed at greater than 5 standard deviations. Every proposed solution that has survived rigorous mathematical scrutiny points in the same direction. The solution that explains dark energy's precise value was proposed before dark energy was discovered, and requires the string, landscape, eternal inflation, and a vast ensemble of universes. The solution that explains the CMB anomalies was published before the measurements it predicted and requires bubble universes that formed alongside ours and physically interacted with us. The solution that resolves the Hubble tension requires vacuum physics that the observable universe cannot generate from its own resources. I have been following this chain for a long time, long enough that I know the feeling when you first hit each one of these results. The momentary hope that this will be the anomaly that gets explained away, and then the recognition that it doesn't get explained away. it gets confirmed again by the next instrument. There is a difference between knowing that anomalies exist in cosmological data and actually sitting with what those anomalies require. The universe cannot explain itself. Every time researchers build a more sensitive instrument and point it at one of these problems, the problem becomes more defined, more statistically significant, more resistant to mundane resolution. The pattern across 6 independent observational datasets and 3 independent theoretical failures, each requiring physics from outside the observable universe, is the evidence. The convergence is the argument. You are not inside a closed, self-explaining system. You are inside a bubble that has been pulled and shaped by things beyond its edge, that sits at a metastable position in a much larger space of possibilities, that cannot account for 68% of its own energy budget, that disagrees with itself about something as basic as how fast it is moving. The universe the evidence describes has been consistent for 30 years. The instruments have only become more precise. Stay with me here, because what I want to say next changes how the evidence feels. The CMB is the oldest light we can detect. It was emitted 380,000 years after the Big Bang, when the plasma of the early universe had cooled enough for electrons to bind to atomic nuclei and for photons to travel freely for the first time. Before that moment, the universe was opaque, a fog so dense that light absorbed and re-emitted instantly, carrying no information across any distance. After that moment, photons escaped in every direction and have been traveling through the expanding universe ever since. The CMB carries the state of the universe at 380,000 years of age. Every temperature variation across its surface is a record of what the universe was like at that specific moment, where matter was slightly denser, where it was slightly thinner, how the plasma was vibrating. It is the earliest accessible image of anything. The interactions that Mersini-Houghton describes happened earlier, during inflation, in the first tiny fraction of a second after the Big Bang, before the plasma, before the CMB was possible. If neighboring universes pressed against ours during that inflationary epoch, the pressure was imprinted into the quantum fluctuations that would later become the density variations that would later become the temperature variations in the CMB. The CMB does not show those interactions directly. It shows the state of a universe that had already been shaped by them. The cold spot is the echo of an echo. The interaction happened during inflation. That interaction shaped the quantum density fluctuations in our forming universe. Those fluctuations evolved and grew over 380,000 years. They froze into the CMB pattern at the moment of last scattering. The photons of the CMB have been carrying that pattern outward in every direction, at the speed of light ever since. Every CMB photon reaching our instruments today left its source 13 billion years ago. It predates every star currently in the sky. It predates our galaxy. It predates our solar system by more than 8 billion years. And encoded in its temperature, in variations of 1/10,000th of a degree, is a memory of what happened before the universe was finished forming. The universe recorded its birth. The bruise on the southern sky is not a statistical accident or a measurement artifact. It is the place where something from outside pressed against our universe while it was still soft, before the CMB even existed as a concept, and the CMB carried the memory of that pressure forward when it finally formed. 13 billion years of that memory traveling outward in every direction simultaneously, reaching galaxy after galaxy, passing through the empty spaces between the stars, eventually reaching our instruments, which we had built to confirm the Standard Model's prediction of a smooth, symmetric, self-contained universe. The map was not smooth. The memory was there. I keep returning to the timing. We built these instruments in the last few decades of human history. The CMB photons have been traveling for 13 billion years. The fact that we were here to receive them at this specific moment in the universe's history and had built instruments sensitive enough to read what they carried and understood what the pattern meant is either an extraordinary coincidence or it is exactly what happens in a universe where minds capable of asking these questions exist at all. Either way, The memory arrived. We read it. Whether we were ready for what it said is a different question. There is a temperature associated with empty, expanding space. This takes a moment to absorb. Temperature, as we normally encounter it, belongs to matter, molecules moving, energy exchanging between particles. A perfect vacuum, the total absence of particles, seems like it should have no temperature at all. Temperature requires something to be hot or cold. Empty space has nothing. But this is not quite right. In the mid-1970s, Stephen Hawking demonstrated that black holes emit radiation due to quantum effects at their event horizons. A black hole has a boundary, the event horizon, from beyond which nothing can escape. The quantum vacuum near that boundary is not actually empty in the way classical physics describes, and the geometry of the horizon converts quantum vacuum fluctuations into real, outgoing particles with a specific thermal spectrum. The black hole has a temperature. Gary Gibbons and Hawking extended this reasoning in 1977. A universe expanding under a positive cosmological constant also has a horizon, a cosmological boundary beyond which information cannot reach an observer, and that horizon also carries an associated temperature. The temperature is extraordinarily small, far smaller than anything ever measured in a laboratory by many orders of magnitude. But it is not zero. In 2004, a physicist named Andreas Albrecht at the University of California, Davis, and Lorenzo Sorbo at the University of Massachusetts worked through a consequence of this temperature that neither found comfortable to publish. A thermal environment, even one at an extremely low temperature, can, in principle, produce any configuration of matter given enough time. Random thermal fluctuations can, over sufficiently long timescales, assemble molecules, then cells, then complete organisms. The probability of any specific complex configuration arising by chance is vanishingly small per attempt. But in a universe expanding forever, the number of attempts is not finite. The de Sitter temperature persists indefinitely. Fluctuations keep occurring over timescales that make any number we can name seem brief. Include among the configurations that thermal fluctuations can produce, given enough time, a complete, functioning, conscious brain assembled by random quantum fluctuations in the de Sitter vacuum, with internally consistent false memories of a life it never lived. Such a brain would, for the brief interval of its coherent existence before dissipating back into the vacuum, experience itself as a real observer in a real universe. Its internal experience would be indistinguishable from the experience of a biological brain that actually grew and developed. Albrecht and Sorbo followed this chain to its conclusion. Physicists, including Sean Carroll, refined the analysis in the years that followed. The conclusion is this: biological observers, like us, require an improbable chain of conditions, a universe with the right constants, billions of years of stellar evolution producing heavy elements, planetary formation, the origin of life, billions more years of biological evolution, contingent and fragile at every step. Each link in that chain is a filter, a random fluctuation that assembles a complete brain with false memories. Requires none of that chain. It requires only a long enough time and the persistent small temperature of the de Sitter vacuum. Over a sufficiently long future, the number of observers produced by random fluctuation grows without bound. The number of observers produced by the full biological chain does not grow at the same rate. Eventually, random observers dominate. In a universe expanding forever under dark energy, exactly the universe the Standard Model describes, the most common form of conscious experience in all of cosmic history will be an accident. Sean Carroll at the California Institute of Technology spent years working on what the Boltzmann brain result actually means for cosmology. His 2017 paper, titled "Why Boltzmann Brains Are Bad," addresses an attitude he had observed in the community, treating phantom observer production as an interesting philosophical curiosity rather than a hard constraint on theoretical models. Carroll's argument begins from a simple premise. Start with a cosmological model. The model makes predictions about the history and future of the universe. One of those predictions is the rate at which different kinds of observers appear throughout the universe's history. If the model predicts that random fluctuation observers will eventually vastly outnumber biological observers, then, according to the model's own accounting, the typical observer in the universe is a random fluctuation. You are an observer. The model applies to you. The model predicts you are more likely to be a random fluctuation than a biological being. According to the model, you are right now statistically far more likely to be a quantum accident assembled moments ago in the de sitter vacuum, with false memories of everything you believe you have experienced, than to be a biological observer who evolved in an ordered universe over billions of years. The objection forms fast. You have direct, continuous, detailed experience of your own past. You remember learning, growing, making choices. Every moment of experience feels causally connected to the moment before it. Surely this sustained experience of continuity is itself evidence that you are a real biological observer rather than a momentary phantom. Here is why that objection does not hold. A Boltzmann brain, assembled by random quantum fluctuation would, as part of its assembled configuration, include internally consistent false memories of exactly this kind of continuity. The memories are part of the brain's physical state. A brain assembled with the memory of a continuous life, of learning and connection and cause and effect, is a brain in a particular physical configuration. That configuration is no different in kind from any other possible configuration. The random fluctuation produced everything, the brain and all its memories simultaneously, as a single coherent physical state. Every feeling of certainty you have right now about your own continuous existence is consistent with being a biological observer in a real universe. It is equally consistent with being a fluctuation assembled moments ago, complete with those feelings and those memories. Introspection cannot separate the two cases. Every sensation of continuity, every memory you are accessing, every conviction that the world around you is consistent and real, both cases produce exactly this experience. The biological observer and the phantom observer have the same internal phenomenology at any given moment. Carroll's point is not that you should believe you are a Boltzmann brain. His point is about what the model predicts. The model we use to describe the universe's history and future, the model that has passed every observational test we have designed for it, predicts that the majority of observers it produces are phantoms. If that prediction is correct, the observers who built and tested the model were probably phantoms too. The science is probably phantom science. The tests the model passed were probably phantom tests. A model that predicts you cannot trust it is a model with a serious problem. Carroll named this failure mode cognitive instability. A cosmological model is cognitively unstable if it predicts that the observers within it are mostly random fluctuations, because those observers' science is probably not a reliable investigation of external reality. The logic holds together tightly. If Boltzmann brains dominate the population of observers in the universe, then most of the minds that have ever thought about physics are Boltzmann brains. Most of the scientific papers ever written are written by Boltzmann brains. Most of the conclusions ever reached by systematic theoretical work are Boltzmann brain conclusions. A Boltzmann brain assembled by random fluctuation in the de sitter vacuum is not running reliable inference about external reality from sense data gathered over a lifetime. It is running internally consistent computation over fabricated inputs, and everything it concludes is a random fluctuation of apparent reasoning. A theory that predicts most observers are hallucinating has cut the ground from under itself. What makes this genuinely difficult, rather than a puzzle to be set aside, is that the standard model of cosmology is extraordinarily successful. The CMB power spectrum predicted by the standard model matches the measured power spectrum across dozens of angular scales. The distribution of matter in the universe, the web of galaxy clusters and filaments and voids, matches the model's predictions for how gravity assembles structure over billions of years. The expansion history of the universe from the Big Bang to the present is described by the Standard Model with a precision that exceeds almost every other predictive framework in science. Every test we have thrown at it has confirmed it. The model works. It works with a consistency and precision that is hard to overstate. The same assumptions that make it successful also require a positive cosmological constant, an eternally expanding de Sitter space, and the persistent Gibbons-Hawking temperature that eventually produces phantom observer dominance. These are not separate predictions bolted onto the model. They follow directly from the same underlying equations that describe the CMB and the large-scale structure of matter. Accept the model's success, and you accept its Boltzmann brain prediction. Accept the Boltzmann brain prediction, and you have reason to distrust the model's success. Carroll was clear that this is not a tolerable state. Any cosmological model that produces Boltzmann brain dominance should be rejected on these grounds, even if it passes every observational test available, because the observational tests were conducted by observers who, according to the model, were probably phantoms. The model fails, a condition more fundamental than empirical fit. It destroys the epistemic foundation that makes empirical testing meaningful. The model that has been our best tool for understanding the universe, the model that gave us the history of cosmic expansion, the formation of the CMB, the conformation of dark energy, that we have spent more than a century building and testing, predicts that the observers doing the building and testing probably cannot be trusted. It works, and it says that its working is probably a coincidence of hallucinated mathematics. Every chapter of evidence gathered in this investigation confirms a framework that, taken to its logical end, undermines every chapter. 3 proposed solutions to the Boltzmann brain problem exist in the peer-reviewed literature. Working through each one matters, because where they lead is the final piece of the chain this investigation has been building. The first solution: the universe does not expand forever. If the de Sitter phase of expansion ends before Boltzmann brains accumulate to dominance, the problem dissolves. The thermal temperature of the de Sitter vacuum disappears when the cosmological constant goes to 0 or becomes negative. The infinite future of phantom fluctuations is replaced by a finite future, possibly followed by a collapse, possibly followed by another kind of physics entirely. This requires a mechanism that terminates the de Sitter phase. The mechanism does not exist within the Standard Model. No field, no particle, no known interaction produces a transition out of the de Sitter phase. The solution requires new physics with no current observational footprint. The second solution, the quantum vacuum in eternally expanding de Sitter space, does not actually produce functioning observers the way the standard calculation describes. Perhaps the mathematical framework breaks down at extreme timescales. Perhaps quantum gravity modifies the vacuum in ways that suppress the production of observer configurations. This cannot be ruled out, and it also has no current support. The solution requires that our understanding of quantum field theory in curved spacetime is wrong in a regime that no instrument can currently test. It proposes a failure of known physics without specifying the mechanism. Stand back from the 3 options. The first requires new physics that does not yet exist. The second requires revising quantum field theory in ways no one has managed. The third requires the multiverse. Every escape from the Boltzmann brain problem either invokes physics nobody has found or confirms that the universe is vastly larger and stranger than anyone in the last century would have accepted. There is no small fix available. There is no adjustment within the existing framework that resolves it. The model that describes the universe with extraordinary precision has produced a conclusion that can only be escaped by going far outside everything we currently know. The exits from the Boltzmann brain problem are the same exits the CMB anomalies require. They are the same exits the cosmological constant problem requires. They are the same exits the Hubble tension requires. Every thread in this investigation, followed to its end, arrives at the same place. A universe that is one component of something much larger, something that operates at scales and by rules that the observable universe alone cannot contain. Assemble the chain from the beginning. The oldest light we can measure shows 5 distinct anomalies, all pointing toward the same region of sky, confirmed across 2 independent satellite missions and 20+ years of analysis. The hemisphere of the sky, facing that direction, carries more large-scale structure than the opposite hemisphere by a statistically impossible margin. The universe's 2 largest coherent features, structures spanning billions of light-years, align along the same axis. A physicist named Laura Mersini-Houghton published predictions for the location and magnitude of the largest anomaly from multiverse mathematics before the measurements she was predicting were completed. A team led by Christopher Hirata identified statistical evidence for 4 separate bubble collision scars in the same region of sky where theory said they should be. Hundreds of billions of galaxy clusters are drifting toward a gravitational source that does not exist within the observable universe. Alexander Kashlinsky at NASA has spent 20 years refining this measurement. Every refinement has confirmed the signal. Dark energy, the force accelerating the expansion of all space, has no source in any physics currently understood. The theoretical prediction for its value misses the observed value by a factor of 10 to the 120th power. The only calculation-based framework that resolves this discrepancy, without invoking undocumented fine-tuning, requires a string, landscape of universes from which ours nucleated. Steven Weinberg predicted the observed dark energy value from this framework in 1989. The measurement confirmed his prediction in 1998. The quantum field that gives every particle its mass, that makes atoms structurally possible, that makes you physically possible, sits in a metastable configuration. The true ground state of the Higgs field exists at a lower energy than the current vacuum. A bubble of that ground state can nucleate anywhere in space and expand at the speed of light. Butazzo and collaborators confirmed the metastability with CERN particle mass data in 2013. The early universe and the current universe disagree about how fast everything is moving, by more than 5 standard deviations, confirmed by the James Webb Space Telescope in 2023. Every resolution of this tension requires physics outside the standard model, new vacuum behavior, landscape-level mechanisms, or an interaction before recombination that the observable universe cannot generate from its own resources. A cosmological model that fits all of this data and fits it with extraordinary precision predicts that the most common form of consciousness in the universe's long future will be phantom minds assembled by random quantum fluctuation in the de Sitter vacuum. The same model predicts that the scientists who built it and tested it were statistically likely to be phantoms themselves. The model succeeds empirically. It destroys its own epistemological foundation. Every one of these threads, followed to its logical end, arrives at the same address, something outside the observable universe, something that has a mass, a direction, a gravitational reach, something that pressed against our universe while it was still forming and left a permanent record in the oldest light, something that set the vacuum energy of our universe at its precise value, something that positioned the Higgs field at a metastable resting point rather than the floor, something that makes the 2 measurements of expansion rate disagree because the universe, between its earliest accessible state and the present, passed through something the model of an isolated system cannot describe. Every instrument we have aimed at the universe's largest scales for 30 years has sent back the same message. The universe is leaking. The edge is a surface, and through it, the outside has already reached us. Whatever is outside has already touched us. We are carrying its mark in the oldest light we can see. There is a question I keep coming back to. We built these instruments in the last few decades of human history. We are one species, on one small rocky body, orbiting one ordinary star in the outer region of one galaxy, among hundreds of billions. We have been technologically capable of probing the large-scale structure of the universe for perhaps a century. The CMB photons reaching our detectors have been traveling for 13 billion years. Against the full timeline of the universe, our period of observation represents an interval so brief it requires scientific notation to describe. And in that brief interval, using instruments we built from the materials available on this one small planet, we detected the marks, the bruise in the southern sky, the gravitational pull from beyond the horizon, the metastable flaw beneath all the physics we know, the mismatch between two different readings of how fast reality is moving. Consider what it would have taken for us to miss these signals. Instruments a little less sensitive, the anomalies landing just inside the error bars instead of outside them. A few more decades before the Hubble tension data was gathered, we would have had a smooth, symmetric, self-contained picture of a closed universe that explained itself from the inside. Most of what I have been describing in this investigation would have remained hidden, consistent with standard predictions, generating no alarm in any data pipeline. We would not have known we were sitting at the edge of something. We happened to be here at the moment the instruments were sensitive enough. We happened to build the satellites and aim them at the right questions. We happened to have theorists like Mersini Houghton, who published predictions before the measurements confirmed them, which meant the confirmation could not be dismissed as post hoc pattern matching. We happened to have the James Webb Space Telescope operating at exactly the moment the Hubble tension needed the definitive test that ruled out instrumental error. I don't know what to do with that timing. It might mean nothing. It might be the selection effect that the anthropic principle describes. Observers who exist to notice these things exist only in universes where the conditions allowed them to form. And the same conditions that allowed them to form are the conditions that the evidence is pointing toward. The fact that we're here to see the evidence may be inseparable from the fact that the evidence exists. What I do know is this: the universe encoded the answer in its oldest light. It has been broadcasting that answer outward in every direction at the speed of light for 13 billion years. It passed through empty space, through the formation of galaxies, through the births and deaths of generations of stars, through the formation of our planet and the entire history of life. Through every century of human civilization, it passed through all of that and kept going, undistorted, carrying its 1/10,000th of a degree variation in temperature until it reached our instruments. The signal is patient. It does not care whether we are ready. Whether we know how to live with what it says is something the signal cannot help us with. The CMB photons reaching your instruments right now left their source before our galaxy existed. Every second that passes, more of them arrive. The universe is still broadcasting. Whatever is beyond the observable edge, whatever has mass and direction and gravitational reach, whatever shaped the density fluctuations that eventually became the temperature pattern in the oldest light, is still there. The signal from it is still traveling. The pull from it has not changed. The flaw beneath the Higgs field is still lower than where the field is sitting. The expansion is still accelerating. The two measurements of expansion rate still disagree. None of this has resolved. None of it is moving toward resolution. Each year, the instruments get more sensitive, and each year, the anomalies become more defined, more statistically confirmed, more precisely inconsistent with a universe that can explain itself from the inside. The research is still running. The data is still coming in. Whatever is leaking through the edge is still leaking. The cosmologists who have spent their careers on these problems have not found the small fix. The standard model's internal resources remain insufficient. The outside ingredient is still required and still unidentified. I have spent a long time following this chain. Following it was not comfortable. Every step led somewhere the previous step hadn't prepared me for. The cold spot was supposed to be a statistical accident. The dark flow was supposed to resolve into noise. The cosmological constant problem was supposed to have a clever local solution. The Hubble tension was supposed to close when the instruments got better. Vacuum decay was supposed to be a timeline so long it required no serious attention. The Boltzmann brain problem was supposed to be philosophy, not physics. Each of those doors closed. The chain kept going. The universe has been trying to tell us something for 13 billion years. We finally built instruments sensitive enough to hear it. We heard it. And the message, read carefully, says that the universe is not alone. Whatever is beyond the edge has already reached us. Whatever left the bruise in the southern sky, whatever is pulling the clusters, whatever set the parameters of all known physics, made contact during our formation and left a permanent record in the oldest light, which means we are not alone in that light either. Every second that passes, more CMB photons arrive at our instruments. The universe's edge is receding faster than light can cross it. Everything beyond the horizon is getting further away forever. The message is the only thing that got through before the window closed. It got through in the temperature variations of ancient light, in the asymmetry of the sky, in the motion of galaxy clusters across the largest scales we can probe. The light keeps coming.